Imagine peering into a Hubble Telescope image from 2004, scanning a patch of sky where galaxies should be evenly distributed, but instead, you notice a faint, serpentine glow-bending light in ways no model predicted. This wasn't a glitch, nor a known cosmic phenomenon. It was an anomaly so subtle, it lingered in the margins of a dataset forgotten by most astronomers. The observer, a former scientist on a crowded train commute, didn't realize they'd stumbled upon a clue that could rewrite our understanding of dark matter. What appeared as a ghostly arc of light wasn't just a trick of optics, it was the faint imprint of invisible matter warping spacetime, its gravitational pull stretching light from distant galaxies into a pattern no theory had yet explained. This accidental discovery, buried in a decades-old image, hints at dark matter's elusive structure, offering a rare glimpse into the invisible scaffolding holding the universe together. And it all began with a single, unremarkable glance at a forgotten dataset. In the quiet hum of a morning train commute, a former scientist paused to examine an old Hubble Space Telescope image. What they found, a faint, intricate pattern across the cosmos, could rewrite our understanding of dark matter. This accidental discovery, buried in decades-old data, hints at a hidden structure in the universe that might finally reveal the elusive substance's secrets. Let me explain how this unexpected observation has sparked a new chapter in the search for dark matter. Dark matter is one of the greatest mysteries in modern astrophysics. Scientists know it exists because of its gravitational effects on visible matter, like galaxies and stars. Without dark matter's invisible pull, galaxies wouldn't hold together, and the universe as we know it wouldn't exist. Yet, despite its overwhelming influence, dark matter doesn't emit, absorb, or reflect light. It's like a ghost in the cosmos, detectable only through its gravitational fingerprints. For decades, researchers have tried to map its distribution, but the challenge has always been that it's invisible. Now, this discovery suggests a new way to trace its presence. The Hubble Space Telescope has been observing the universe for over 3 decades, capturing images of distant galaxies, nebulae, and cosmic phenomena. Its vast archive contains millions of such images, many of which have been studied extensively. But this particular image, taken years ago, had been overlooked. The scientist, whose identity remains private, was reviewing old data when they noticed something unusual. The image showed a cluster of galaxies, but within the cosmic web of light, there was an unexpected pattern, something that didn't align with existing models of how dark matter should behave. The pattern resembled a faint, tangled web of light, stretching across the image like threads in a cosmic tapestry. At first glance, it looked like a normal galaxy cluster, but closer inspection revealed an anomaly. The distribution of light didn't match the expected gravitational effects of visible matter alone. The scientist realized this might be a signature of dark matter's influence. In other words, the way light bent around massive objects in the image suggested that dark matter was shaping the structure of the universe in ways previously unobserved. To understand why this is significant, we need to revisit how scientists study dark matter. One common method involves observing how light bends around massive objects, a phenomenon called gravitational lensing. When light from a distant galaxy passes near a massive object, like a galaxy cluster, the gravity of that object warps spacetime, causing the light to curve. This distortion creates a kind of cosmic lens, bending the light into arcs or brightening the background galaxy. By analyzing these distortions, scientists can infer the distribution of mass, including dark matter, in the foreground. In this case, the Hubble image showed a galaxy cluster that acted as a gravitational lens, but the pattern of light bending was more complex than expected. The scientists noticed that the light wasn't just being bent by the visible matter in the cluster. There was an additional, subtle distortion that couldn't be explained by known physics. This extra distortion suggested the presence of dark matter in a specific, structured way. The pattern wasn't random, it was organized, hinting at a larger cosmic structure that dark matter might be forming. This discovery is groundbreaking because it offers a new approach to mapping dark matter. Traditionally, scientists have relied on indirect methods, like gravitational lensing or the motion of galaxies, to infer dark matter's presence. But this pattern in the Hubble image provides a direct visual clue. If dark matter is shaping the light in this way, it means we can study its distribution by analyzing how it bends light across vast cosmic distances. This could lead to more precise maps of dark matter, helping us understand its role in the universe's structure. the implications of this finding are profound. Dark matter is thought to make up about 27% of the universe's total mass energy content, yet its nature remains a mystery. Is it composed of undiscovered particles? Does it interact with ordinary matter in ways we haven't yet detected? This discovery could provide answers. If dark matter is creating these intricate patterns in the cosmic web, it might reveal how it clumps together, forming the scaffolding upon which galaxies and galaxy clusters form. By studying these patterns, scientists might even uncover the fundamental properties of dark matter itself. What makes this discovery even more remarkable is that it came from an old image. Hubble has been operating for over 30 years, and its archive is a treasure trove of data. Many of these images have been studied, but this particular one had been overlooked. The scientists' fresh perspective, combined with advanced computational tools, allowed them to notice something others had missed. This highlights the importance of revisiting old data with new techniques. In science, sometimes the answers are already there, waiting to be rediscovered. The scientific community is now excited about this finding. Researchers are analyzing the Hubble image in greater detail, trying to confirm whether this pattern is a true signature of dark matter or an anomaly. If it is, it could open new avenues for studying dark matter's distribution and behavior. For example, by comparing this pattern to other Hubble images, scientists might identify similar structures across the universe, creating a more comprehensive map of dark matter. This could help answer long-standing questions about how dark matter influences the formation of galaxies and the large-scale structure of the cosmos. One of the most intriguing aspects of this discovery is that it challenges existing assumptions about dark matter's distribution. Current models suggest that dark matter forms vast, diffuse halos around galaxies, but this pattern suggests a more structured, web-like arrangement. If dark matter is forming intricate networks across the universe, it could mean that its behavior is more complex than previously thought. This could lead to new theories about how dark matter interacts with itself and with ordinary matter, potentially even hinting at its fundamental nature. Of course, there's still much work to be done. The scientific process is rigorous, and this finding will need to be independently verified. Other telescopes, like the James Webb Space Telescope, might be used to study similar patterns in greater detail. Additionally, simulations will be run to test whether these patterns could arise from known physics or if they require new explanations. If this discovery holds up, it could mark a turning point in the search for dark matter, offering a tangible way to study its elusive presence. In the end, this accidental discovery underscores the power of curiosity and persistence in science. The scientist who found this pattern wasn't looking for dark matter, they were simply reviewing old data. Yet, their keen eye and willingness to question the familiar led to a breakthrough. This story reminds us that science often relies on unexpected observations, and that even the most well-studied data can hold surprises. As researchers continue to analyze this finding, it may pave the way for a deeper understanding of dark matter and perhaps, one day, unlock the secrets of the universe's invisible scaffolding. The discovery began with a simple act, someone taking a moment to look at an old image, one that had been stored away for years. It wasn't a planned observation, nor was it part of any major research project. Instead, it was a chance gaze, a moment of curiosity, that led to something extraordinary. The image in question was captured by the Hubble Space Telescope, an instrument that has spent decades peering into the cosmos, collecting data that has reshaped our understanding of the universe. But this particular image, taken years earlier, had been overlooked until now. What made it special? It contained subtle patterns that hinted at something beyond the visible, something that science had only begun to grasp: dark matter. The journey to confirm this revelation involved a complex interplay of technology, observation, and analysis, each step building on the last to unravel a mystery that has eluded astronomers for decades. Let's explore how this discovery came to light, and what it means for our understanding of the universe. The Hubble Space Telescope, launched in 1990, has been one of humanity's most powerful tools for observing the cosmos. Its ability to capture high-resolution images of distant galaxies, stars, and nebulae has provided invaluable insights into the structure and evolution of the universe. However, even with its advanced instruments, Hubble has faced challenges. One of the most persistent mysteries it has helped investigate is dark matter, a substance that makes up an estimated 27% of the universe's mass energy content, yet remains invisible to direct observation. Unlike ordinary matter, which interacts through electromagnetic forces and can be seen with telescopes, dark matter only reveals its presence through gravitational effects. Scientists have long sought to map its distribution, but without direct detection, its nature remains elusive. This is where the old Hubble image came into play. The image in question was captured by Hubble's Wide Field Camera 3, WFC3, an instrument designed to capture light across a broad range of wavelengths, from ultraviolet to near-infrared. The WFC3 has been instrumental in studying distant galaxies, including those that formed in the early universe. When the former scientist first examined the image, they noticed something unusual: faint, diffuse structures that didn't align with the expected distribution of visible matter. These structures, though subtle, suggested the presence of something unseen, something that could only be explained by dark matter. But how could they be certain? The answer lay in a combination of advanced observational techniques and decades of theoretical work. To confirm the presence of dark matter, scientists needed to analyze the gravitational effects it exerts on visible matter. This is where the concept of gravitational lensing comes into play. Gravitational lensing occurs when the gravitational pull of a massive object, such as a galaxy or a cluster of galaxies, bends the light from objects behind it. This bending creates distortions in the light, such as arcs or streaks, which can be analyzed to infer the distribution of mass in the foreground object. If dark matter is present, its gravitational influence would cause these distortions, even though it doesn't emit or absorb light. By studying these distortions, scientists can map the distribution of dark matter in the universe. The old Hubble image provided a unique opportunity to apply this technique. The image contained a galaxy cluster, a region where dark matter is expected to be concentrated due to the gravitational pull of massive structures. By analyzing the light from distant galaxies behind the cluster, scientists could detect the subtle distortions caused by the cluster's mass. However, the challenge lay in distinguishing these distortions from other sources of light contamination, such as foreground stars or background galaxies. This required a meticulous process of data analysis, involving sophisticated algorithms and computational power to filter out noise and isolate the gravitational effects of dark matter. The confirmation process also relied on cross-referencing the Hubble data with other observations. For example, the European Southern Observatory's Very Large Telescope, VLT, and the Atacama Cosmology Telescope, ACT, have been used to study the cosmic microwave background, CMB, the faint afterglow of the Big Bang. The CMB provides a snapshot of the early universe and contains imprints of dark matter's distribution. By comparing the Hubble data with CMB observations, scientists could validate their findings and ensure consistency across different methods. This multi-wavelength approach is crucial for confirming the presence of dark matter, as no single observation can provide a complete picture. Another key factor in the discovery was the use of machine learning and artificial intelligence to analyze the vast amounts of data collected by Hubble. These tools allowed scientists to process and interpret images more efficiently, identifying patterns that might have been overlooked by human eyes. For instance, algorithms could detect subtle distortions in the light from distant galaxies, which would then be analyzed to determine the mass distribution of the foreground object. This process, known as weak gravitational lensing, is one of the most promising methods for mapping dark matter. However, it requires immense computational resources and careful calibration to ensure accuracy. The timeline of the discovery also highlights the collaborative nature of modern astrophysics. The initial observation of the Hubble image was made by the former scientist, but the subsequent analysis involved a team of researchers from various institutions. This collaboration was essential, as the complexity of the data required expertise in multiple fields, including observational astronomy, computational analysis, and theoretical physics. The process of confirming the findings took several months, during which the team refined their methods, cross-checked their results, and ensured that their conclusions were robust. This iterative process is a hallmark of scientific discovery, where initial observations are followed by rigorous validation and peer review. The significance of this discovery lies in its potential to shed light on the nature of dark matter. While the findings from the Hubble image provide further evidence of dark matter's existence, they also offer new insights into its distribution and behavior. By studying how dark matter interacts with visible matter and how it influences the structure of the universe, scientists can refine their models and perhaps even uncover its fundamental properties. This could lead to breakthroughs in particle physics, as dark matter is believed to consist of particles that have not yet been directly detected. The discovery also underscores the importance of archival data, old images that, when re-examined with new techniques, can reveal new information about the cosmos. In addition to its scientific implications, the discovery serves as a reminder of the power of serendipity in scientific research. Many of the most groundbreaking discoveries have emerged from unexpected observations or overlooked data. The Hubble image, once deemed irrelevant, became a key piece of evidence in the ongoing quest to understand dark matter. This highlights the value of preserving and re-examining historical data, as future technologies and analytical methods can uncover new insights from the same observations. It also emphasizes the importance of curiosity and open-mindedness in science, where a simple glance at an old image can lead to profound revelations. The journey from the initial observation to the confirmation of the discovery was a testament to the ingenuity and perseverance of the scientific community. It required a combination of advanced technology, rigorous analysis, and interdisciplinary collaboration to transform a chance gaze into a significant breakthrough. As scientists continue to explore the mysteries of dark matter, discoveries like this one will play a crucial role in advancing our understanding of the universe. The Hubble Space Telescope, with its unparalleled ability to capture the cosmos in exquisite detail, remains a vital tool in this endeavor. And as new missions and instruments come online, the potential for further discoveries grows, reminding us that the universe still holds many secrets waiting to be uncovered. On a morning train commute, this former scientist found a stellar surprise in an old Hubble image. This part of our deep dive into chance gaze at old Hubble Telescope image leads to discovery that could reveal dark matter's secrets. Focuses on, go deeper into the underlying science/physics/astronomy that makes this significant. Explain why it matters to our understanding of the universe, in accessible plain language. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For viewers who want to go deeper than this summary, the primary source linked in the description lays out the full technical picture. Findings like this rarely stand alone, they get compared against earlier observations to make sure the pattern holds up under scrutiny. Scientists are still cross-checking the data before drawing firm conclusions, which is exactly the kind of patience that makes space science trustworthy. None of this comes from speculation, it comes from instruments built to measure faint signals that the naked eye could never pick up on its own. It's easy to forget how much coordination sits behind a single headline like this: years of engineering, calibration, and review before anyone announces anything. That's part of why stories like this take time to fully confirm. Good science moves carefully, even when the early results already look remarkable. For decades, the universe has been hiding in plain sight. The very fabric of space, the invisible scaffolding that holds galaxies together, has eluded direct observation. Yet, its presence has been inferred through subtle clues: gravitational pulls that defy expectations, cosmic structures that seem too massive to exist without unseen matter. This mystery, now known as dark matter, has shaped the trajectory of modern astrophysics. Its discovery wasn't a single moment of revelation, but a slow accumulation of anomalies, each one pushing scientists closer to an answer. Let's trace how this enigma unfolded, from the first hints in the 1930s to the breakthroughs that made today's discovery possible. The story begins in the 1930s, when Swiss astronomer Fritz Zwicky first noticed something strange about galaxy clusters. While studying the Coma cluster, he calculated that the visible matter, stars, gas, and dust didn't account for the gravitational forces holding the cluster together. The galaxies were moving too fast for their visible mass to explain. Zwicky proposed a radical idea, that there must be unseen matter, an invisible substance exerting gravity without emitting light. He called it dark matter, though the term wasn't widely used until later. His observations were met with skepticism, as there was no direct evidence to support his claim. But Zwicky's work laid the groundwork for a question that would dominate astrophysics for decades: what holds the universe together if visible matter isn't enough? The next major clue came in the 1970s, when American astronomer Vera Rubin and her colleagues studied the rotation of spiral galaxies. They expected stars farther from a galaxy's center to orbit more slowly, just as planets in our solar system move slower the farther they are from the Sun. But what they found was astonishing: stars at the edges of galaxies moved at the same speed as those near the center. This suggested that there was far more mass in the galaxy than could be seen. The only explanation was that unseen matter, dark matter, was providing the extra gravitational pull. Rubin's work, though initially controversial, became a cornerstone of modern cosmology. It confirmed Zwicky's hypothesis and forced scientists to confront a reality they hadn't anticipated: the universe was made of something they couldn't see. For years, dark matter remained a theoretical construct, a placeholder for the unknown. But as technology advanced, so did the tools to probe its existence. The 1990s brought a turning point with the discovery of the Bullet Cluster, a collision between two galaxy clusters. This event provided a rare opportunity to observe dark matter directly. When the clusters collided, the visible matter, gas and stars, slowed down due to friction, while the dark matter, which doesn't interact with itself or normal matter, passed through unimpeded. By mapping the gravitational lensing effects, scientists could see the invisible mass shaping the light around it. The result was a stunning confirmation: dark matter exists, and it's not just a theoretical concept, it's a real, pervasive force in the cosmos. This breakthrough wasn't just about proving dark matter's existence. It also deepened the mystery. If dark matter is so widespread, why hasn't it been detected yet? The answer lies in its nature. Unlike ordinary matter, dark matter doesn't interact with electromagnetic forces, meaning it doesn't emit, absorb, or reflect light. This makes it invisible to traditional telescopes. Instead, scientists had to rely on indirect methods, measuring gravitational effects, tracking the motion of galaxies, and analyzing the cosmic microwave background. The 2000s saw a surge in such studies. The cosmic microwave background, CMB, the afterglow of the Big Bang, provided a crucial clue. By studying tiny fluctuations in the CMB, scientists could map the distribution of matter in the early universe. These observations confirmed that dark matter made up about 27% of the universe's total mass energy content, with ordinary matter accounting for just 5%. The remaining 68% was even more mysterious: dark energy, a force driving the universe's accelerated expansion. As the 21st century progressed, the search for dark matter intensified. Experiments like the Large Hadron Collider and underground detectors such as Xenon and LUX aimed to detect dark matter particles directly. However, these efforts yielded no conclusive results. The lack of direct detection hasn't discouraged scientists; instead, it has pushed them to refine their methods. The Hubble Space Telescope, launched in 1990, has played a pivotal role in this quest. Its ability to peer into the distant universe has allowed astronomers to study galaxy formation, gravitational lensing, and the distribution of mass on cosmic scales. Over the years, Hubble has captured images of galaxy clusters, star-forming regions, and distant quasars, each providing new insights into the universe's structure. Yet, the mystery of dark matter remained elusive, a puzzle that required a fresh perspective. The recent discovery, born from a chance gaze at an old Hubble image, represents a new chapter in this long history. While the Hubble telescope has been instrumental in mapping dark matter's gravitational effects, this particular finding suggests that there might be more to uncover. The image, originally captured for a different purpose, revealed patterns that hinted at dark matter's subtle influence. These patterns, perhaps invisible to earlier analyses, could provide clues about its distribution or even its properties. This discovery doesn't just add to the existing body of knowledge, it opens the door to new questions. If dark matter's behavior can be observed in ways previously unimagined, it might one day lead to a deeper understanding of its nature. The journey to unravel dark matter's secrets has been long, but each step has brought us closer to a universe that is both vast and enigmatic. And now, with tools like Hubble, the next discoveries may be just around the corner. Dark matter remains one of the most profound mysteries in modern astrophysics. For decades, scientists have known that the visible universe, stars, galaxies, planets, and all the matter we can see accounts for only about 5% of the total mass-energy content of the cosmos. The rest, a mysterious substance called dark matter, exerts gravitational pull but does not interact with light or other forms of electromagnetic radiation. This invisible scaffolding holds galaxies together, bends light from distant objects through gravitational lensing, and shapes the large-scale structure of the universe. Yet, despite its overwhelming influence, dark matter has eluded direct detection. Its nature remains a question mark, with theories ranging from it being a collection of undiscovered subatomic particles to something entirely different from what we currently imagine. The discovery sparked by that chance gaze at an old Hubble image adds another layer to this enigma, raising questions that could reshape our understanding of the cosmos. One of the most perplexing aspects of dark matter is its role in the universe's gravitational dynamics. Observations of galaxy clusters, such as the famous bullet cluster collision, have shown that the visible matter in these systems doesn't align with the gravitational effects detected by gravitational lensing. This suggests that dark matter exists independently of the ordinary matter we see, yet its exact composition and behavior remain elusive. Theories like the weakly interacting massive particles, WIMPs, or axions have been proposed to explain dark matter's properties, but none have been confirmed by direct detection experiments. The lack of a definitive answer has led to a vibrant scientific debate. Is dark matter truly a form of matter we've yet to identify, or is it a manifestation of a deeper, more fundamental principle of physics that we have yet to grasp? The discovery from the Hubble image, while seemingly accidental, hints at a potential breakthrough. The scientist's observation, perhaps a peculiar distribution of light or an unexpected pattern in the data, could challenge existing models of dark matter's distribution or behavior. For instance, if the image revealed structures that suggest dark matter interacts with itself in ways not predicted by current theories, it might indicate that dark matter is not a simple, uniform substance but something more complex. Alternatively, it could point to a flaw in our understanding of how dark matter influences the universe's large-scale structure. Such findings would not only refine our models but also open new avenues for research, potentially leading to experiments or observations that could finally detect dark matter's elusive nature. Yet, even if this discovery provides new insights, many questions remain unresolved. One of the most persistent debates in dark matter research is whether it is truly a form of matter or if it represents a fundamental force or property of space itself. Theories like modified Newtonian dynamics, (MOND), propose that dark matter's effects are not due to unseen particles but rather a modification of the laws of gravity on cosmic scales. While MOND can explain some observations, it struggles to account for others, such as the behavior of galaxy clusters and the cosmic microwave background. The existence of dark matter as a separate entity versus a redefinition of gravity remains a contentious issue, with no consensus among scientists. The Hubble image's findings could tip the balance in this debate, offering evidence that either supports or refutes these competing frameworks. Another unresolved mystery is the nature of dark matter's interactions. If dark matter is composed of particles, they must interact through some force, but the exact mechanism remains unknown. Current experiments, such as those using underground detectors or cosmic rays, have yet to find conclusive evidence of dark matter particles. The absence of direct detection has led some physicists to consider alternative explanations, such as dark matter being a form of energy rather than matter. However, this idea faces challenges in reconciling with existing observations, particularly those involving gravitational lensing and the distribution of galaxy clusters. The discovery from the Hubble image might provide clues about these interactions, suggesting that dark matter behaves in ways that current models have not anticipated. For example, if the image revealed subtle distortions in light that imply dark matter clumps together in unexpected ways, it could indicate that its particles have properties we have yet to consider. The implications of such a discovery extend beyond dark matter itself. If the Hubble image's findings challenge existing assumptions about dark matter's behavior, they could also affect our understanding of the universe's evolution. The distribution of dark matter is thought to have played a crucial role in the formation of galaxies and large-scale structures. If dark matter interacts with itself or with ordinary matter in ways not yet understood, it could mean that the processes shaping the cosmos are more complex than previously believed. This complexity might also influence how we interpret other cosmic phenomena, such as the motion of stars within galaxies or the distribution of dark matter in the early universe. The Hubble image's findings could thus have far-reaching consequences, prompting a re-evaluation of long-held theories about the universe's history and future. Despite the excitement surrounding potential breakthroughs, the scientific community remains cautious. The universe is vast and complex, and a single observation, no matter how intriguing, must be scrutinized through rigorous analysis. The discovery from the Hubble image, while promising, would need to be verified through independent studies and corroborated by other observations. Scientists must also consider alternative explanations for the anomaly, ensuring that the findings are not the result of observational errors or biases. This process of validation is essential in science, as it helps distinguish between genuine discoveries and statistical flukes. The journey from an accidental observation to a confirmed breakthrough is often long and fraught with uncertainty, but it is this process that drives scientific progress. The unresolved questions surrounding dark matter also highlight the limitations of our current observational tools. While the Hubble Space Telescope has provided invaluable insights into the cosmos, its ability to detect dark matter is constrained by its reliance on light. Dark matter, by its very nature, does not emit, absorb, or reflect light, making it invisible to traditional methods. This limitation underscores the need for new technologies and approaches to study dark matter. Future missions, such as the James Webb Space Telescope or ground-based observatories equipped with advanced gravitational lensing techniques, may offer new ways to probe the invisible. Additionally, experiments designed to detect dark matter particles, such as those using underground detectors or particle accelerators, continue to push the boundaries of what is possible. The Hubble image's discovery could serve as a catalyst for these efforts, inspiring new experiments and collaborations that bring us closer to unraveling the dark matter mystery. Even with all these challenges, the pursuit of understanding dark matter remains one of the most compelling endeavors in science. The discovery from the Hubble image, while accidental, exemplifies how serendipity can play a role in scientific breakthroughs. It reminds us that the universe is full of surprises, and that our understanding of it is constantly evolving. The questions surrounding dark matter are not just about what we don't know, they are about how we can continue to explore the unknown. As scientists refine their models, develop new technologies, and analyze data from ever more sophisticated instruments, the hope is that one day, the mysteries of dark matter will be unraveled. Until then, the search continues, driven by curiosity, perseverance, and the relentless pursuit of knowledge. As the story of this unexpected discovery unfolds, it becomes clear that the journey to unravel dark matter's mysteries is far from over. The initial glimpse of something unusual in an old Hubble image has sparked a cascade of questions, and now scientists are turning their attention to the next frontier of exploration. Future missions, cutting-edge instruments, and ambitious observations are already in the pipeline, each designed to build on this breakthrough. These efforts will not only test the validity of the discovery but also push the boundaries of what we know about the universe's invisible scaffolding. Let's take a closer look at the tools and strategies that could soon shed light on dark matter's elusive nature. One of the most promising avenues lies in the upcoming Euclid mission, a collaboration between the European Space Agency and NASA. Scheduled for launch in 2023, Euclid will carry a powerful visible and near-infrared telescope equipped with a high-resolution camera and a spectrograph. Its primary goal is to map the distribution of dark matter across the cosmos by studying the gravitational lensing effect, how light from distant galaxies bends around massive structures. By analyzing these distortions, Euclid will create a detailed map of dark matter's invisible web, potentially confirming or refining the patterns observed in the Hubble image. This mission represents a significant leap forward, as it will cover a much larger area of the sky and gather data with unprecedented precision. If the initial discovery hints at a new way to detect dark matter, Euclid's findings could either validate those insights or reveal entirely different mechanisms at play. Complementing Euclid's efforts will be the Nancy Grace Roman Space Telescope, NASA's next-generation observatory set to launch in the mid-2020s. Named after the pioneering astrophysicist, this telescope will inherit Hubble's legacy while introducing revolutionary capabilities. Its primary instrument, the Wide-Field Instrument, will capture vast swaths of the sky in a single exposure, allowing astronomers to study the cosmic web on an unprecedented scale. The Roman telescope will also focus on weak gravitational lensing, a technique that measures how dark matter distorts the light of background galaxies. By combining data from multiple surveys, scientists hope to create a three-dimensional map of dark matter's distribution, revealing how it interacts with visible matter and influences the large-scale structure of the universe. If the Hubble discovery points to an anomaly in dark matter behavior, the Roman telescope's broader dataset could provide the context needed to understand its significance. Meanwhile, the James Webb Space Telescope, already in operation, is offering new perspectives on dark matter through its ability to peer deeper into the universe than ever before. While Webb's primary mission is to study the early cosmos and the formation of galaxies, its infrared capabilities also make it a powerful tool for detecting subtle gravitational effects. By observing distant galaxy clusters and their interactions, Webb can help refine models of how dark matter influences the motion of visible matter. For instance, if the Hubble discovery suggests that dark matter behaves differently in certain environments, Webb's observations of high-redshift systems could either support or challenge those ideas. The telescope's ability to detect faint light from ancient galaxies also means it can trace how dark matter has shaped the universe's evolution over billions of years, providing a historical context for any anomalies detected. Beyond space-based observatories, ground-based projects are also playing a critical role in the search for dark matter. The Vera C. Rubin Observatory in Chile, set to begin operations in the 2020s, will conduct the Legacy Survey of Space and Time (LSST), a decade-long project to map the sky in exquisite detail. The LSST will capture images of billions of galaxies, allowing astronomers to study how dark matter affects their distribution and motion. By combining data from LSST with other surveys, scientists can build a more comprehensive picture of dark matter's role in the universe. Additionally, the observatory's ability to detect transient phenomena, such as gravitational lensing events, could uncover new clues about dark matter's behavior. These ground-based efforts, while limited by atmospheric interference, will provide a crucial complement to space missions like Euclid and Roman, offering a multifaceted approach to the problem. Another exciting development is the growing use of machine learning and artificial intelligence in analyzing astronomical data. As the volume of data from missions like Hubble, Euclid, and Roman continues to grow, traditional methods of analysis may struggle to keep pace. Researchers are now training algorithms to identify subtle patterns in images and simulations that might indicate new properties of dark matter. For example, if the Hubble discovery points to a previously unknown interaction between dark matter and ordinary matter, machine learning tools could help sift through vast datasets to find similar signals. These techniques are already being used to detect dark matter candidates in particle physics experiments, and their application to observational astronomy could revolutionize how we approach the problem. By automating the search for anomalies, scientists can focus their efforts on the most promising leads, accelerating the pace of discovery. However, the quest to understand dark matter is not without its challenges. One of the biggest hurdles is the sheer scale of the problem. Dark matter is invisible, doesn't emit or absorb light, and interacts with ordinary matter only through gravity. This makes it incredibly difficult to study directly, requiring scientists to rely on indirect methods like gravitational lensing and galaxy rotation curves. Even with missions like Euclid and Roman, the data they collect will need to be meticulously analyzed to extract meaningful insights. Moreover, the universe is vast and complex, and what appears to be an anomaly in one part of the cosmos might be a statistical fluke rather than a fundamental property of dark matter. Scientists must remain cautious, ensuring that any conclusions drawn from the Hubble discovery are supported by a broader body of evidence. To address these challenges, researchers are also turning to simulations and theoretical models to test their hypotheses. By creating detailed computer models of the universe's structure, scientists can predict how dark matter should behave under different scenarios. If the Hubble discovery suggests a deviation from current models, these simulations can help identify what kind of modifications might be necessary. For instance, some theories propose that dark matter could consist of particles that interact in ways not yet observed, while others suggest that our understanding of gravity itself might need revision. By comparing simulation results with observational data, scientists can refine their models and narrow down the possibilities. This interplay between theory and observation is crucial for advancing our knowledge, as it ensures that any breakthroughs are grounded in rigorous scientific inquiry. The potential implications of this discovery are staggering. If the Hubble image indeed points to a new way of detecting dark matter, it could pave the way for entirely new technologies and methodologies. For example, the development of more sensitive detectors or the refinement of gravitational lensing techniques might become priorities. Additionally, the discovery could challenge existing theories about dark matter's role in the universe, forcing scientists to reconsider long-held assumptions. In some cases, it might even hint at the existence of entirely new particles or forces that have yet to be discovered. These possibilities underscore the importance of continued exploration, as each new piece of evidence brings us closer to understanding the invisible forces that shape our cosmos. As we look to the future, it's clear that the search for dark matter is a collaborative effort spanning multiple disciplines and continents. Astronomers, physicists, engineers, and data scientists are all contributing to this grand endeavor, each bringing their expertise to the table. The Hubble discovery, while remarkable in its own right, is just one thread in a much larger tapestry of research. By combining the strengths of space-based observatories, ground-based surveys, and advanced computational tools, scientists are building a more complete picture of the universe's hidden architecture. This collective effort ensures that no anomaly, no matter how small, will be overlooked, and that every clue, no matter how faint, will be pursued with the same curiosity and determination that led to this groundbreaking moment. In the coming years, the scientific community will be watching closely for results from missions like Euclid, Roman, and the LSST, as well as for new insights from web and ground-based observatories. These efforts will not only test the validity of the Hubble discovery but also expand our understanding of dark matter's role in the universe. Whether the findings confirm existing theories, reveal new phenomena, or challenge our assumptions, they will undoubtedly shape the next chapter in the story of dark matter. As we continue to look skyward, one thing is certain: the universe still holds many secrets, and the tools we build today will be the keys to unlocking them. For now, the journey has only just begun, and the possibilities are as vast and mysterious as the cosmos itself. So there's this thing about science: sometimes the biggest breakthroughs start with a question no one expected. Imagine this: a former scientist, probably in the middle of a mundane morning commute, scrolling through an old Hubble Telescope image. What they saw wasn't just another galaxy or nebula. It was something entirely different. A pattern, a structure, a whisper from the cosmos that hinted at dark matter's hidden hand. This isn't just another story about serendipity. It's a reminder that even in the vast, uncharted darkness of space, there are clues waiting to be found if we're just looking in the right way. Let me break this down. First, the discovery itself: a faint, ghostly glow in a Hubble image that didn't fit the expected models. It wasn't light from stars or gas, but something else entirely. The team realized it might be the faint, indirect signature of dark matter itself. Dark matter, that invisible scaffolding holding galaxies together, has eluded direct detection for decades. This finding suggests a new way to map it, using the way it bends light around massive objects. But here's the twist: the image was decades old. It wasn't a new observation, but a forgotten one. This highlights a growing trend in astronomy, revisiting old data with fresh eyes and new tools. The Hubble Telescope has been imaging the universe for over 30 years, and every image is a potential goldmine. What's fascinating is that this discovery wasn't planned. It was a chance gaze, a moment of curiosity that turned into a breakthrough. That's the power of persistence and the importance of keeping archives alive. Now, why does this matter? Dark matter makes up about 27% of the universe, yet we've never seen it. It doesn't interact with light, so we can't observe it directly. But its gravitational pull shapes galaxies and clusters. This new clue suggests dark matter might not be as uniform as we thought. If this faint glow is a signature of its distribution, it could mean dark matter is clumpier, more structured than current models predict. That's a big deal because it challenges our understanding of how the universe formed. It also opens the door to new experiments. Scientists might now look for similar patterns in other Hubble data, or even in images from other telescopes. But here's the thing: this isn't just about dark matter. It's about how science works. It's about the idea that even in the most meticulously planned missions, the unexpected can reveal truths we've missed. The Hubble telescope was designed to answer specific questions about distant galaxies and cosmic expansion. Yet, in the quiet of a train station, a scientist found a way to probe one of the greatest mysteries of all. This story isn't just about a discovery. It's about the human element of science, the curiosity, the patience, and the willingness to question what we think we know. So what does this mean for the future? Well, it means there's more to explore, more data to analyze, more questions to ask. And for those of you watching, this is just one example of how science thrives on curiosity and the courage to look beyond the obvious. If you've enjoyed this deep dive, hit that subscribe button to join us for daily explorations of the cosmos. And if you've got your own theories or questions about dark matter, dark energy, or the secrets hidden in old telescope images, drop them in the comments. Because science isn't just about answers, it's about the journey and the endless possibilities that lie ahead.